NEC Section 250.30. A1 requires that all grounding electrodes of a building or structure be connected together to form a grounding electrode system. NEC Section 250.30. A2 requires that the grounding electrode system shall be connected to the equipment grounding system. NEC Section 250.30. A3 requires that the grounding electrode system shall be connected to the grounded conductor of the service. NEC Section 250.30. A4 requires that the grounding electrode system shall be connected to all metal underground water pipe systems within or entering the buildings. NEC Section 250.30. A5 requires that the grounding electrode system shall be connected to the gas piping system within or entering the buildings. The new building, although structurally separated from the existing building, is still considered part of the same building or structure. Therefore, the steel of the new building must be bonded to the steel of the existing building to comply with NEC Section 250.30. A1. The new building has its own grounding electrode, a U for ground. This electrode must be connected to the grounding electrode system of the existing building to comply with NEC Section 250.30. A1. Water, telephone, gas, and other piping run between the buildings provide a conductive path. This path could allow electrical current to flow between the two buildings, creating a safety hazard. Bonding the steel of the new building to the steel of the existing building helps prevent this. The NEC emphasizes the creation of a comprehensive grounding electrode system for buildings and structures to ensure electrical safety and minimize potential hazards. The requirements outlined in NEC Section 250.30. A. Specifically subsections 1 through 5 detail the essential components and connections needed for a robust grounding system. Firstly, NEC Section 250.30. A1 mandates that all grounding electrodes present within a building or structure must be interconnected to form a unified grounding electrode system. This means that whether it's a ground rod, ground ring, or a concrete encased electrode, also known as a U for ground, all these elements must be electrically connected. This interconnection aims to establish a common ground potential throughout the building, minimizing voltage differences and reducing the risk of electrical shock or equipment damage. Secondly, NEC Section 250.30. A2 stipulates that this comprehensive grounding electrode system must be connected to the equipment grounding system. The equipment grounding system is a network of conductive pathways designed to provide a low impedance path for fault current to return to the source. This connection ensures that any fault current within the electrical system can quickly and safely flow back to the source, stripping the overcurrent protection devices such as circuit breakers or fuses to de-energize the circuit and prevent prolonged fault conditions. Thirdly, NEC Section 250.30. A3 dictates that the grounding electrode system must be connected to the grounded conductor of the service. The grounded conductor, typically the neutral conductor in a residential or commercial electrical system, is intentionally connected to ground at the service entrance. This connection provides a reference point for the electrical system and helps to stabilize the voltage levels. By connecting the grounding electrode system to the grounded conductor, the NEC ensures that the entire electrical system is effectively grounded, minimizing the risk of voltage fluctuations and electrical noise. Fourthly, NEC Section 250.30. A4 addresses the importance of grounding metal underground water pipe systems. Metal water pipes can serve as excellent grounding electrodes due to their extensive contact with the earth. The NEC requires that all metal underground water pipe systems within or entering a building be connected to the grounding electrode system. This connection not only enhances the grounding capabilities of the system, but also helps to prevent corrosion of the water pipes by minimizing stray currents. Fifthly, NEC Section 250.30. A5 extends the grounding requirements to gas piping systems. Similar to water pipes, gas pipes can also serve as conductive pathways within a building. The NEC mandates that the gas piping system within or entering a building be connected to the grounding electrode system. This connection helps to prevent the buildup of static electricity on the gas pipes and reduces the risk of ignition in the presence of flammable gases. Now, considering a scenario where a new building is structurally separated from an existing building, it is crucial to understand how the NEC requirements apply. Even though the buildings are structurally independent, the NEC considers them as part of the same structure for grounding purposes if they are electrically interconnected. This means that the steel of the new building must be bonded to the steel of the existing building to comply with NEC section 250.30. A1. This bonding ensures that both buildings share a common ground potential, preventing voltage differences and minimizing the risk of electrical hazards. Furthermore, if the new building has its own grounding electrode, such as a UFO ground, this electrode must be connected to the grounding electrode system of the existing building. This interconnection reinforces the grounding network and ensures that both buildings are effectively grounded. The presence of water, telephone, gas, and other piping running between the buildings further emphasizes the need for bonding. These pipes can act as conductive pathways, allowing electrical current to flow between the buildings. Without proper bonding, this current flow can create a safety hazard. Bonding the steel of the new building to the steel of the existing building mitigates this risk by providing a low impedance path for fault current to flow back to the source, tripping the overcurrent protection devices. In summary, the NEC requirements for grounding and bonding are designed to create a safe and reliable electrical system. By interconnecting all grounding electrodes, connecting to the equipment grounding system, grounding the neutral conductor, and bonding metal, water, and gas pipes, the NEC ensures that buildings are effectively grounded and protected from electrical hazards. In situations where new buildings are structurally separated from existing buildings, it is crucial to maintain electrical continuity through bonding to comply with the NEC and ensure the safety of occupants and equipment. Additional explanation of grounding and bonding. Grounding and bonding are two distinct but interconnected concepts in electrical safety. Grounding refers to connecting an electrical circuit or equipment to the earth, providing a low impedance path for fault current to flow back to the source. Bonding, on the other hand, refers to connecting non-current carrying metal parts of an electrical system together to create an electrically conductive path. The purpose of grounding is to protect people from electrical shock by providing a path for fault current to flow back to the source, tripping the overcurrent protection devices. Without grounding, a fault current could flow through a person who comes into contact with an energized metal part, resulting in a serious or fatal electrical shock. The purpose of bonding is to minimize voltage differences between metal parts, reducing the risk of electrical shock. When metal parts are not properly bonded, voltage differences can occur due to inductive coupling, capacitive coupling, or ground faults. If a person comes into contact with two metal parts with different voltage potentials, they could experience an electrical shock. The NEC provides detailed requirements for grounding and bonding in Article 250. These requirements cover everything from the size and type of grounding and bonding conductors to the methods for connecting them. It is important to follow these requirements carefully to ensure the safety of people and property. Grounding electrode system. A grounding electrode system is a network of interconnected grounding electrodes that provide a connection to the earth. The NEC recognizes several types of grounding electrodes, including ground rods, ground rings, concrete encased electrodes, and metal or underground water pipes. The grounding electrode system must be connected to the equipment grounding system and the grounded conductor of the service. This connection ensures that the entire electrical system is effectively grounded. Equipment grounding system. The equipment grounding system is a network of conductive pathways that provide a low impedance path for fault current to return to the source. The equipment grounding system includes equipment grounding conductors, metal conduits, metal raceways, and other metal enclosures. The equipment grounding system must be connected to the grounding electrode system and the service equipment. This connection ensures that fault current can quickly and safely flow back to the source, tripping the overcurrent protection devices. Bonding jumpers. Bonding jumpers are used to connect metal parts together to create an electrically conductive path. Bonding jumpers are typically made of copper or aluminum and must be sized according to the NEC requirements. Bonding jumpers are used to bond metal conduits, metal raceways, metal enclosures, and other metal parts of the electrical system. This bonding minimizes voltage differences between metal parts and reduces the risk of electrical shock. U for ground. A U for ground, also known as a concrete encased electrode, is a grounding electrode that is encased in concrete. A U for ground typically consists of a length of bare copper conductor that is embedded in the concrete foundation of a building. U for grounds are very effective grounding electrodes because they have a large surface area in contact with the earth. U for grounds are often used in new construction because they can be easily installed during the foundation pouring process. Importance of bonding in separated structures. When dealing with separate structures, even if they are structurally independent, maintaining proper bonding is paramount for electrical safety. The primary reason is to ensure equipotentiality, which means that all conductive surfaces within and between the structures are at the same electrical potential. This eliminates the risk of voltage differences that can lead to electric shock hazards. Consider a scenario where two buildings are separated by a distance, and each building has its own grounding electrode system. If these grounding systems are not properly bonded together, a difference in ground potential can develop between the two buildings. This potential difference can arise due to various factors, such as differences in soil conductivity, variations in electrical load, or even lightning strikes. If a person were to simultaneously touch a grounded metal object in one building and a grounded metal object in the other building, they could become a conductor for the potential difference, resulting in an electric shock. To mitigate this risk, the NEC requires that the grounding systems of separate structures be bonded together with a bonding conductor. This conductor provides a low impedance path for current to flow between the grounding systems, equalizing the ground potential and minimizing the risk of electric shock. The size of the bonding conductor is determined by the size of the service entrance conductors, as specified in the NEC. In addition to bonding the grounding systems, it is also important to bond any metallic pathways that exist between the separate structures. This includes water pipes, gas pipes, communication cables, and any other metallic conductors that could provide a path for current to flow. Bonding these metallic pathways ensures that they are also at the same electrical potential, further reducing the risk of electric shock. The bonding of metallic pathways is typically accomplished by installing bonding jumpers between the metallic components. These jumpers should be sized appropriately for the expected current flow and should be installed in accordance with the NEC requirements. It is important to note that the bonding requirements for separate structures can be complex and may vary depending on the specific circumstances. Therefore, it is always recommended to consult with a qualified electrical engineer or electrician to ensure that the bonding is performed correctly and in accordance with the applicable codes and standards. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Understanding ground potential difference. Ground potential difference, or GPD, refers to the voltage difference between 2 points on the Earth's surface. This difference in potential can arise due to various factors, including variations in soil conductivity, differences in electrical load, and lightning strikes. GPD can pose a significant safety hazard, particularly in situations where there are separate structures with independent grounding systems. When a GPD exists between two structures, a person who simultaneously contacts grounded metal objects in both structures can be exposed to a dangerous voltage. This is because the person's body becomes a conductor, allowing current to flow from the higher potential to the lower potential. The magnitude of the current flow depends on the potential difference and the resistance of the person's body. Even a small potential difference can result in a painful or even fatal electric shock. To mitigate the risks associated with GPD, it is essential to ensure that all grounding systems are properly bonded together. Bonding provides a lower impedance path for current to flow, equalizing the ground potential and minimizing the voltage difference between structures. In addition to bonding, it is also important to consider the location of grounding electrodes. Grounding electrodes should be located as close as possible to the equipment they are intended to ground. This minimizes the length of the grounding conductor and reduces the impedance of the grounding path. In situations where there are multiple grounding electrodes, they should be spaced apart to avoid overlapping spheres of influence. Overlapping spheres of influence can reduce the effectiveness of the grounding system and increase the risk of GPD. Another factor to consider is the soil conductivity. Soil conductivity varies depending on the type of soil, moisture content, and temperature. Areas with low soil conductivity may require more extensive grounding systems to achieve adequate grounding. It is also important to protect grounding electrodes from corrosion. Corrosion can increase the resistance of the grounding path and reduce the effectiveness of the grounding system. Grounding electrodes should be made of corrosion-resistant materials or should be coated with a corrosion-resistant coating. Finally, it is important to regularly inspect and test grounding systems to ensure that they are functioning properly. Grounding system testing should be performed by a qualified electrician using calibrated test equipment. Testing should include measuring the impedance of the grounding path and verifying the continuity of all grounding connections. By following these guidelines, it is possible to minimize the risks associated with GPD and ensure the safety of people and equipment. The role of the grounding electrode conductor (GEC). The grounding electrode conductor, or GEC, plays a vital role in an electrical system by connecting the system's grounded conductor, typically the neutral, to the grounding electrode. This connection establishes a low impedance path to earth, ensuring that the electrical system is properly referenced to ground potential. The primary function of the GEC is to provide a path for fault current to flow back to the source in the event of a ground fault. When a ground fault occurs, current flows from an energized conductor to a grounded metal part. The GEC provides a low impedance path for this fault current to return to the source, tripping the overcurrent protection device, such as a circuit breaker or fuse, and energizing the circuit. Without a properly sized and installed GEC, the fault current may not be sufficient to trip the overcurrent protection device, resulting in a prolonged fault condition that could lead to equipment damage, fire, or electric shock. The NEC specifies the minimum size requirements for the GEC in Table 250.66. The size of the GEC is based on the size of the service entrance conductors. The larger the service entrance conductors, the larger the GEC must be. The GEC must be made of copper or aluminum and must be protected from physical damage. The GEC must be connected to the grounding electrode using approved methods such as exothermic welding, listed connectors, or bolted connections. It is important to ensure that the GEC is properly installed and maintained to ensure the safety and reliability of the electrical system. A loose or corroded GEC connection can significantly increase the impedance of the grounding path, reducing its effectiveness. Regular inspection and testing of the GEC are essential to identify and correct any problems. In addition to providing a path for fault current, the GEC also helps to stabilize the voltage of the electrical system. By connecting the neutral to ground, the GEC helps to prevent voltage fluctuations and reduce the risk of electrical noise. This is particularly important in sensitive electronic equipment, such as computers and medical devices. The GEC also plays a role in protecting against lightning strikes. When lightning strikes a building, a large amount of current flows through the electrical system. The GEC provides a path for this current to flow to ground, minimizing the risk of damage to equipment and the building structure. In summary, the GEC is a critical component of an electrical system, providing a path for fault current, stabilizing voltage, and protecting against lightning strikes. Proper installation and maintenance of the GEC are essential for ensuring the safety and reliability of the electrical system. The importance of low impedance grounding path. A low impedance grounding path is essential for ensuring electrical safety and protecting equipment from damage. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. A high impedance grounding path can impede the flow of fault current, preventing overcurrent protection devices from tripping quickly and effectively. This can result in prolonged fault conditions, leading to equipment damage, fire, and electric shock hazards. A low impedance grounding path, on the other hand, allows fault current to flow quickly and easily back to the source, tripping the overcurrent protection device and energizing the circuit. This minimizes the duration of the fault and reduces the risk of damage or injury. There are several factors that can affect the impedance of a grounding path, including the size and type of grounding conductors, the length of the grounding conductors, the quality of the grounding connections, and the soil conductivity. To achieve a low impedance grounding path, it is important to use appropriately sized grounding conductors. The NEC specifies the minimum size requirements for grounding conductors in Table 250.122. The size of the grounding conductor is based on the size of the overcurrent protection device protecting the circuit. The larger the overcurrent protection device, the larger the grounding conductor must be. It is also important to minimize the length of grounding conductors. The longer the grounding conductor, the higher the impedance. Grounding conductors should be run as directly as possible to the grounding electrode, avoiding unnecessary bends or loops. The quality of grounding connections is also critical. Loose or corroded connections can significantly increase the impedance of the grounding path. Grounding connections should be made using approved methods such as exothermic welding, listed connectors, or bolted connections. All connections should be clean, tight, and free of corrosion. Soil conductivity can also affect the impedance of the grounding path. Areas with low soil conductivity may require more extensive grounding systems to achieve adequate grounding. Soil conductivity can be improved by adding soil amendments such as bentonite clay, or by installing ground rods deeper into the earth. Regular inspection and testing of grounding systems are essential to ensure that they are functioning properly. Grounding system testing should include measuring the impedance of the grounding path and verifying the continuity of all grounding connections. Any problems identified during testing should be corrected promptly. In summary, a low impedance grounding path is essential for electrical safety and equipment protection. By using appropriately sized grounding conductors, minimizing the length of grounding conductors, ensuring high quality grounding connections, and addressing soil conductivity issues, it is possible to achieve a low impedance grounding path that will effectively protect people and equipment from electrical hazards. Understanding the NEC grounding tables. The National Electrical Code, or NEC, contains several tables that are essential for properly grounding electrical systems. These tables provide guidance on conductor sizing, grounding electrode selection, and bonding requirements. Understanding these tables is crucial for ensuring electrical safety and compliance with the NEC. One of the most important grounding tables is Table 250.66, which specifies the size of the grounding electrode conductor, or GEC, for AC systems. The GC connects the grounded conductor, typically the neutral, to the grounding electrode. The size of the GC is based on the size of the service entrance conductors. The larger the service entrance conductor is, the larger the GC must be. Table 250.122 specifies the size of equipment grounding conductors, or EGs, for AC circuits. EGC provide a low impedance path for fault current to flow back to the source, tripping the overcurrent protection device. The size of the EGC is based on the rating of the overcurrent protection device protecting the circuit. The larger the overcurrent protection device, the larger the EGC must be. Table 250.102. C1 specifies the size of bonding jumpers for services. Bonding jumpers are used to connect metal enclosures, raceways, and other metal parts of the electrical system together to create an electrically conductive path. The size of the bonding jumper is based on the size of the service entrance conductors. Table 250.53 outlines the requirements for grounding electrode systems. This table specifies the types of grounding electrodes that are permitted, the minimum length and depth requirements for grounding electrodes, and the methods for connecting grounding electrodes. The NEC also contains tables that provide guidance on bonding requirements for specific types of equipment, such as swimming pools, spas, and agricultural buildings. These tables specify the size and type of bonding conductors that are required and the methods for connecting them. It is important to note that the NEC tables are minimum requirements. In some cases, it may be necessary to use larger conductors or more extensive grounding systems to achieve adequate grounding. It is always recommended to consult with a qualified electrical engineer or electrician to determine the appropriate grounding requirements for a specific installation. In addition to the tables, the NEC also contains explanatory material that provides additional guidance on grounding and bonding. This explanatory material can be helpful for understanding the intent of the code requirements and for resolving complex grounding issues. In summary, the NEC grounding tables are essential tools for properly grounding electrical systems. Understanding these tables and the associated explanatory material is crucial for ensuring electrical safety and compliance with the NEC. Importance of regular inspections and testing. Regular inspections and testing of electrical grounding systems are crucial for ensuring their continued effectiveness and safety. Over time, grounding systems can degrade due to corrosion, physical damage, loose connections, or changes in soil conditions. Regular inspections and testing can identify these problems before they lead to dangerous situations. Visual inspections should be performed at least annually to check for signs of corrosion, damage, or loose connections. Grounding conductors, connections, and electrodes should be carefully examined for any signs of deterioration. Any problems identified during the visual inspection should be corrected promptly. Grounding system testing should be performed by a qualified electrician using calibrated test equipment. Testing should include measuring the impedance of the grounding path and verifying the continuity of all grounding connections. Impedance testing measures the total opposition to current flow in the grounding path. A high impedance value indicates a problem with the grounding system, such as a loose connection or corroded conductor. Continuity testing verifies that all grounding connections are intact and that there are no open circuits in the grounding path. The frequency of grounding system testing depends on the type of installation and the environmental conditions. In general, testing should be performed at least every 3 years, or more frequently in corrosive environments or in installations with sensitive electronic equipment. The results of all inspections and tests should be documented and kept on file. This documentation provides a record of the grounding system's performance over time and can be used to identify trends or patterns that may indicate potential problems. It is important to note that grounding system testing should be performed in accordance with industry standards and best practices. The Institute of Electrical and Electronics Engineers, or IEE, publishes several standards that provide guidance on grounding system testing. In addition to regular inspections and testing, it is also important to perform grounding system maintenance as needed. This may include tightening connections, replacing corroded conductors, or adding additional grounding electrodes. Proper grounding system maintenance can extend the life of the grounding system and ensure its continued effectiveness. In summary, regular inspections and testing of electrical grounding systems are essential for ensuring electrical safety and protecting equipment from damage. By identifying and correcting problems early, it is possible to prevent dangerous situations and maintain a safe and reliable electrical system.